This is the next video in the chapter on electronic structure and periodic properties. We have now talked about quantum numbers n, l, and m sub l, and in this video we'll talk about the last one, m sub s. We'll add in the last line to our table, n sub s, and the s is for spin. So this number is the only one that isn't going to be an integer. The only allowed values for m sub s, in our case, are going to be plus 1/2 or minus 1/2. And this quantum number is going to tell us about the pairing or the spin. We are just going to use a lot of paper in this chapter and have lots of space to draw pictures. Okay, so the m sub s value is different from all of the other values. The first three values gave specific information to tell us which orbital an electron lived in, and this quantum number is going to tell us which electron in that orbital we are trying to talk about. As we said, each orbital can hold up to 2 electrons. But each of those electrons is different. There's something about them that makes them not quite the same. This is something we've detected with measurements. When measuring those Balmer lines that we showed that helped us discover what quantized energy was for electrons, as our technology improved, we were able to zoom in and get very high resolution lines. And we saw that for each line, it was actually split into a tiny, tiny pair of lines, one for each electron. So there was something about the 2 electrons living in the same orbital that was slightly different. And it's a little bit difficult to describe because it doesn't relate to anything that we have in the normal macroscopic world. So the way that we model what this difference is by comparing the electron to the planet Earth. So we model it as a spin around an axis. This is like when Earth spins around its axis and it changes from night to day on Earth. So for those of you who are in physics, this is going to look really familiar to you. We're going to pretend the electron is a particle. We use the particle view in this case. And if we say that the particle is spinning in a particular direction, this way or this way, if we use the right-hand rule, we'll see that the force is going up for this one, and it's going down for this one. So we can describe one of the possible states of an electron as spin up and one of them as spin down. Now this isn't exactly how it works, and the electron is not actually spinning, but this is sort of the closest way of describing what's happening, the easiest way to understand. So we're going to call the spin up electron, we're going to give that an m sub s value of positive 1/2. And we're going to give the spin down an m sub s value of negative 1/2. For complicated quantum mechanical reasons that we don't need to know right now. And this is the last quantum number. And that leads us to a principle written by Pauli that sort of sums up everything we need to know about how to describe the electron address. And Pauli's principle says, if an orbital contains 2 electrons, as we were just discussing, then we know one of those electrons must be spin up and one of those electrons must be spin down. In other words, two electrons that are living in the same house have to be of opposite spins. If they're occupying the same space, they have to be opposite spins so that they can stand to be that close to each other. So we can summarize what it looks like when electrons have all the quantum numbers in common. Down here at the bottom. Electrons with the same values for N and L and M sub L and M sub S must be the same electron. They have the same energy, they have the same location, they have the same orientation, they are the same electron. This address can only describe one electron. So this is where maybe our analogy about the street address breaks down a little bit, because in this analogy, only one person can live in a house. Same house, same electron. So if you have the same 4 quantum numbers, you have the same quantum address. So this is how we can specify where one particular electron is located. If we just want to specify what space it's in, we will just give the first 3 quantum numbers, because that space can hold up to 2. But if we want to talk about a specific electron in a specific orbital, we would give all 4 quantum numbers. So now we know how to use all 4 quantum numbers, N, L, M sub L, and M sub S. And now it is time to blow your mind by showing you how those quantum numbers were secretly in the periodic table this whole time. The periodic table is kind of like the map that the addresses refer to. Periodic table is the map we use to find an electron's address. Emphasis on map. So let's dive into that. So the periodic table is a table. So it has horizontal rows or periods and vertical columns or families. And it also is divided into sections, which I've emphasized by drawing it in this sort of boxy format. So over here, one row, which is also called a period, hence the name periodic table. There is one row in the table for every value of n, the principal quantum number, or for every shell. So there are 1, 2, 3, 4, 5, 6, 7 rows or periods in our current version of the periodic table. And each of those refers to a different shell. So there are 7 electron shells for elements that we have currently discovered. Okay, over here, there is one sort of block for every possible value of L. So one block for each subshell. We'll use green for this one. There's one block for each subshell. So over here on the left, the smallest block, that one is for the L equals 0 subshell. So we call this the S block. Over here on the right, this one is the next biggest block. So that one is for L equals 1. We call this the P block. Here in the center, this is the next longest one. This is for L equals 2. This is called the D block. And then down here in the extended edition that doesn't quite fit, it belongs right here in the table. This one is for L equals 3. This part is called the F block. And we'll talk more about that in the next video when we start filling in electrons. So we did rows. We also need to do the columns. There is one column, which we call a family. One family for every electron in a subshell. And let's do blue for that one. So each electron in a subshell gets its own row. So if you remember, the L equals 0, those s orbitals, they can only hold 2 electrons. And there are 2 columns in the s block. The p orbitals, there were 3 different flavors. So 6 electrons can be held in one p subshell. And there are 6 columns in the p block. For the d block, there were 5 different flavors of d orbitals. They can each hold 2 electrons, so that's 10 electrons total in a d subshell. And there are 10 columns in the d block. And for the f block, there are 7 different flavors. They can each hold 2 electrons, and there are 14 columns in this section. So the periodic table was secretly a treasure map this whole time. You may not have known how to use it. So now that we finally know about all 4 quantum numbers, let's do a couple of examples of trying to figure out some of the quantum numbers from other ones. So if you were given a table like this, where some of the names, n values, l values, and m sub l values were listed for a particular orbital, a question might say something like fill in the missing values. So you should be able to figure out the missing information based on what is listed. So let's start with this first line here. All we know about this first orbital is that it's called the 5p orbital. So we remember that this notation means the 5 in the front refers to the principal quantum number. So the principal quantum number for that one is 5. The letter is the angular quantum number. It is our L value. And P is the second value. So the first value for L is 0. The second value for L is 1. So the L equals 1 is the p orbital. And then for p orbitals, there were 3 different flavors. So the possible flavors were L equals -1, or 0, or +1. So we don't know which one it's talking about because there isn't a picture, but it could be any of those 3. Okay, so then here's the second line. This is going to be a different orbital. Let's see if we can figure out the missing information for the second one. We are told that this second orbital has an n value of 3 and an L value of 2. So that will tell us how to make that name. When we make the name, we put the n number at the beginning, and then we follow that with the L letter. So L equals 2 corresponds to the letter D. So this is going to be one of the 3 d orbitals. And remember that there are 5 different flavors of d orbitals. So the possible m sub L values could be -2, or -1, or 0, or 1, or 2. There should be 5 different possible values there. So that is everything you need to know about quantum numbers, how to define where an electron is located, how much energy it has, and which orbital it lives in. In the next set of videos, we'll talk about electronic structure and how to fill electrons in to these orbitals.